Hi, my name's Brad. I'm an applications engineer with Keithley Instruments and Tektronix. This video will introduce the features of Keithley's I-V Tracer, an app for our 2400 series of graphical source measure units that allows you to trace current voltage characteristics of two-terminal devices, similar to how a traditional curve tracer like a Tektronix 576 or 370 would work. I-V Tracer takes over the front panel display of your source measure unit and allows you to directly control the output voltage or current with the front panel knob while plotting current versus voltage in real time. This allows you to quickly verify specifications, identify points of failure, or even compare two similar devices. Let's dive right in, shall we? First, I'll demonstrate how to get to I-V Tracer after it's installed. On the latest firmware of your source measure unit, you'll find this apps icon added to the menu. You can find a variety of apps for this screen on Tek.com if you want. Right now, I only have I-V Tracer installed. On clicking the Run button, the app starts and takes over the user interface to turn my SMU into a two-terminal curve tracer. Let's hook up a device. I've connected that diode at the bottom so we can trace its characteristic curve. Turning the output on, you can see a magenta dot appear that will always be the last measured point. Turning the knob allows me to change the output level while plotting the I-V curve. Moving slower changes the output in smaller steps, like you might expect. If I increase the level too high, you'll see a yellow limit warning appear as the output level is restricted. We'll see how to adjust that limit later. If I hold at a single point, you can see the exact measured value continue to update in the lower right, since the output stays on after all. I set my upper voltage bound a little too high for this curve. You can tell because of all the extra space on the right. I'll use the auto scale function to make my curve fill the entire screen. Then I'll adjust the increased zoom by pinching slightly too. Now that I've zoomed my display in, the output step size of one knob click has been adjusted accordingly. That is, as you zoom in, the step size decreases. I'll zoom in a little bit more too. This really helps when you want to carefully trace into a device's operating region, like looking at the knee of this diode curve. The minimum output resolution depends on which 2400 series graphical SMU you're using. For a 2450 like this one, the minimum resolution is 500 nanovolts or 500 femtoamps when sourcing current. Hitting the reset button will reset the display, but keep your output level and other settings intact. Next, I'll show you how to compare two different device curves. First, I'll turn the output off and press the compare button to save this curve as a reference. It's now stored in the instrument's memory. I'll change to a different diode now. I've already traced its curve as you can see. Pressing compare again, I'll enable the compare mode. And I can see my reference show up in blue. It overlays on my current trace and matches any zooming that I perform. This mode is really helpful for looking at diode behavior on transistors, when you might want to compare leakage curves among a batch of devices. I want to show you the settings screen and different polarities now. As I go to the menu button, you can see the menu screen is completely different from normal. This settings screen holds most all the settings you'll care about. There's a shortcut to get here from the main screen. You can see there's settings for outputting either voltage or current, the peak output level, measurement limits, effectively the power limit, selecting 2-wire or 4-wire sense, and the polarity setting. What I'm going to do now is change the polarity from positive DC to negative DC. This means I'll be sourcing a negative voltage instead of a positive one. I'll also change my peak output level from 2 volts to 10 volts. This is because I want to see the Zener voltage of this diode I have connected, which should be around negative 9 volts. I'll trace up or down to it now. Notice I still move the knob clockwise. Think of the knob as controlling a percentage of your output level instead of changing the output level directly. I should really zoom in on this knee here, but I want to show you other polarities still. Now I've kept the same Zener diode, but I've swapped my instrument to a 2461 SMU. This SMU has dual 1 megasample per second digitizers that allow for much faster measurements, including enhanced pulse behavior and an AC mode. I'll take the settings shortcut and you can see the option to enable pulsing here. This mode is very helpful to prevent self-heating effects from changing your curve. Enabling it allows you to adjust the pulse width. What I'll show you now though is the AC polarity. This polarity outputs a sine wave about 0 volts. The level you set with the knob now becomes the amplitude of this wave. The frequency matches your line frequency. When sourcing current, the instrument sources a cosine wave instead. That'll take a separate video to go into though. Anyway, I'll change my peak level back to 10 volts so my AC wave now has a maximum amplitude of 10 volts from 0. Going home, I'll turn the output on and ramp up the amplitude. You can see my wave is now centered at 0. On the positive end, my device is protected from a dangerous amount of power with my current limit setting. On the negative end, I can continue ramping until I see the full behavior of this Zener diode. I-V Tracer comes with a dedicated Kickstart app that you can use to transfer data to your computer. Simply click the Collect button in the bottom left to bring over the curve from your SMU. Kickstart offers you a table view for looking directly at measurements and a graph view for more visual analysis. You can, of course, export the data from here to another program if you wish. This Kickstart app is also how you install I-V Tracer. Look for our other video on that topic. I-V Tracer can be used anywhere your SMU can, using either the front or rear terminals, which makes it a very portable solution. Remember that if you want to use voltages above 40 volts, you'll need to use a test fixture that can satisfy interlock. This is to prevent accidentally touching any hazardous voltages. That's particularly relevant for the 2470, which has a 1000 volt range, very helpful for tracing into reverse breakdown voltages. For most cases though, I find a simple breadboard like this one, or even some clip-on leads are sufficient. I hope this video has been helpful. You can install a trial of I-V Tracer to your own instrument by connecting it to Kickstart, Keithley's benchtop instrument control software. Or you can learn more by visiting tech.com/Keithley I-V Tracer. Thanks for watching.
Find out more at Vicom's website.